Picture a sky not with one star, not even two or three, but six blazing suns, locked in an intricate cosmic dance. This isn't science fiction. It's the reality of sextuple star systems, some of the rarest and most bewildering structures in our universe. Astronomers have spent decades unraveling their secrets, and what they've discovered defies imagination. These systems aren't just celestial oddities, they're laboratories of chaos and wonder, where gravity weaves impossibly complex orbits and stars behave in ways that challenge everything we thought we knew. If you've ever stared up at the night sky and felt that tug of curiosity, buckle up, because what we're about to explore will reshape how you see the cosmos. So, what exactly makes sextuple star systems so extraordinary? Imagine six massive stars, each with its own gravitational pull, all bound together in a delicate balance. Some orbit so closely they almost touch, while others whirl around each other at staggering distances. The forces at play here are so extreme that even the most advanced simulations struggle to predict their movements. And yet, against all odds, these systems exist scattered across the galaxy like cosmic puzzles waiting to be solved. For scientists, they're a goldmine of questions. How do they form? How do they survive without tearing themselves apart? And what can they teach us about the birth and death of stars? But the real magic lies in the strange, almost surreal discoveries astronomers have made. From stars that eclipse each other in mind-bending patterns to unexplained energy fluctuations that hint at unseen companions, sextuple systems are full of surprises. Some even host planets' worlds bathed in the light of multiple suns, where sunsets and sunrises would be a spectacle beyond human comprehension. As we journey through these 30 astonishing revelations, you'll witness the universe at its most unpredictable and awe-inspiring. This isn't just a story about stars, it's a reminder that the cosmos thrives on mystery, and every answer we find only leads to more breathtaking questions. Among the countless stars in our galaxy, one system stands out as the first confirmed sextuple TYC 7037-89-1. Nestled in the constellation Eridanus, roughly 1900 light-years from Earth, this celestial marvel wasn't discovered all at once. Instead, it revealed itself piece by piece, like a cosmic Russian nesting doll. Initially spotted by NASA, a transiting exoplanet survey satellite, or TESS, the data showed something impossible. A star that dimmed not once, not twice, but in an intricate pattern of dips and flares. When astronomers dug deeper, they realized they weren't looking at one star or even two. They'd stumbled upon six. What makes TYC 7037-89-1 so mind-bending is its structure. Picture three pairs of binary stars, each duo locked in a tight orbit, eclipsing each other from our viewpoint. But here's where it gets wild. Those three pairs themselves whirl around a common center of gravity, creating a hierarchical dance of staggering complexity. The innermost binaries complete their orbits in just 1.5 days, while the outer pairs take years. It's like a clockwork mechanism built by the universe itself, precision layered atop chaos. Scientists were flawed. Systems like this weren't supposed to exist. The gravitational forces should have ripped them apart, yet here they were, stable and shining. Even more astonishing, the stars themselves are far from identical. Some are hotter, larger, and brighter than our sun, while others are smaller and cooler. This mix of sizes and temperatures creates a celestial light show unlike anything else. Flares, eclipses, and energy surges that rewrite the rules of stellar behavior. But the real question is, how did this system form? Current theories suggest it's the product of multiple generations of star birth, where dense gas clouds fragmented into pairs that later became gravitationally entwined. It's a cosmic game of chance, a 1 in a billion alignment of conditions, and for astronomers, TYC 7037-89-1 isn't just a curiosity, it's a blueprint. By studying its rhythms and disruptions, we're learning how gravity shapes the most extreme stellar families and what that means for the fate of other multiples hiding in the cosmos. The gravitational ballet of TYC 7037-89-1 is nothing short of cosmic poetry, but with a chaotic twist that leaves scientists both fascinated and baffled. Imagine 6 performers on a stage where the choreography changes every second, each star tugging on the others with its own rhythmic force. The innermost binary stars whirl around each other so fast they complete an orbit in less than 2 days, close enough that their atmospheres almost brush together. Meanwhile, the other 2 binary pairs trace much wider, slower paths, creating a nested hierarchy of motion where speed and scale collide. What's truly mind-blowing is how these stars don't spiral into catastrophe. Gravitational physics tells us that multi-star systems should be unstable like a game of Jenga with too many blocks pulled out. Yet here, the stars maintain their delicate balance. The secret lies in their precise distances and orbital resonances, where the gravitational nudges between them sync up like gears in a clock. When one pair completes a certain number of orbits, another pair matches it in a way that cancels out disruptive forces. It's as if the universe has solved its own equation for harmony, but one wrong move could unravel it all. Modeling this dance is a nightmare for astronomers. Supercomputers crunching endless lines of code still struggle to simulate the system's long-term behavior. Tiny uncertainties like the exact mass of one star or a slight tilt in an orbit snowball into wildly different futures. Some simulations show the stars gradually drifting apart over millennia. Others predict violent collisions. The reality, we're watching a real-time experiment in cosmic stability, and every new observation adds another piece to the puzzle. What's even more surprising is how these stars influence each other's lives. The tight binaries transfer mass between them, creating flares and eruptions that ripple through the system. The outer stars, though more distant, act like gravitational anchors, subtly tweaking the inner orbits over time. It's a reminder that in sextuple systems, no star is an island. Everyone plays a role in the survival of the whole. And somehow, against all odds, this chaotic family has found a way to endure. Now picture this, a cosmic light show so baffling that even seasoned astronomers initially scratched their heads in disbelief. Among the many mysteries of TYC 7037-89-1, none were more perplexing than its overlapping eclipses. Normally, when one star passes in front of another, we see a predictable dip in brightness, a celestial wink. But in this system, the eclipses don't play by the rules. With 3 binary pairs all orbiting at different speeds and angles, their shadows cross paths in ways that create a kaleidoscope of unpredictable dimming and flickering. At first glance, the data looked like noise, a jumbled mess of light curves that defied explanation. The key to unraveling this puzzle, patience and precision. Astronomers turned to NASA, a transiting exoplanet survey satellite, or TESS, which had already spotted the system's initial irregularities. But TESS alone couldn't decode the chaos. Teams combined its observations with high-resolution spectroscopy from ground-based telescopes, peeling back layer after layer of interference. What emerged was a revelation: the eclipses weren't random. They were the result of an intricate celestial choreography, where the innermost binaries eclipse each other every 1.5 days, while the outer pairs cast overlapping shadows at much longer intervals. The result, a light curve that looks like a heartbeat with multiple rhythms, some rapid, some slow, all intertwined. To make sense of it, researchers relied on computational models so advanced they bordered on art. By simulating countless orbital configurations, they could finally match the bizarre dips in brightness to actual stellar movements. Imagine trying to separate the sound of 6 orchestras playing at once. Only here, the instruments are stars and the music is written in gravity. The breakthrough came when they realized the system's tilt plays a starring role. Some binaries orbit at slight angles to each other, meaning their eclipses sometimes coincide, sometimes miss entirely, and occasionally graze past in partial obscurations. This cosmic game of shadow tag creates patterns so complex that even now, new surprises emerge with every observation. What's truly remarkable is how these eclipses reveal secrets we'd never see otherwise. The precise timing of each dip exposes the stars' sizes, temperatures, and even hints at their atmospheres. Some eclipses last longer than expected, suggesting one star's gravity is stretching its companion into an egg-like shape. Others show unexpected flares, as if the stars are trading violent bursts of energy mid-eclipse. For astronomers, it's like watching a celestial autopsy. The light curves dissect the system's inner workings in real time. And with each new decode, we're not just learning about one bizarre sextuple family. We're uncovering the hidden rules that govern all multi-star systems, rewriting the textbook one eclipse at a time. Among the many mind-bending quirks of sextuple star systems, one discovery stands out as particularly baffling. Stars in the same cosmic family shouldn't just differ in size or temperature. They should be roughly the same age. After all, conventional wisdom tells us stars in a shared system form from the same collapsing cloud of gas and dust, like siblings born from the same womb. Yet when astronomers analyzed TYC 7037-89-1, they found stars that acted like strangers, some youthful and vibrant, others seemingly older, as if they'd been plucked from different eras of cosmic history. How does this happen? One theory points to stellar capture, a gravitational heist on an unimaginable scale. Imagine a pair of binary stars drifting through space, minding their own business when they pass too close to another star cluster. The gravitational tug-of-war that follows could fling one star away while snagging another, weaving it into the existing system. Over millions of years, this cosmic game of musical chairs might explain why some stars appear older. They weren't part of the original family but were adopted later, carrying the chemical fingerprints of their distant birthplace. But there's another, even stranger possibility: delayed ignition. In dense stellar nurseries, not all gas clumps ignite into stars at the same time. Some might linger as faint, failed stars called brown dwarfs for eons before a nearby supernova's shockwave or a gravitational nudge suddenly compresses them enough to light the fusion furnace. The result, a star that's technically billions of years old but only recently started shining, making it seem younger than its siblings. In sextuple systems, where gravitational interactions are constant, this delayed awakening could explain why some stars appear out of sync. The evidence lies in the star's spectra, the unique chemical barcodes imprinted in their light. Younger stars burn hotter and cleaner, with fewer heavy elements forged by previous generations. Older stars, by contrast, carry the metallicity of an ancient cosmic neighborhood. When telescopes scrutinized the sextuple system, they found this exact mismatch. Some stars showed the pristine signature of youth, while others bore the marks of a long, turbulent life. This discovery doesn't just rewrite the rules of star formation. It suggests these systems are far more dynamic than we ever imagined. They're not static families but evolving celestial ecosystems where stars can be stolen, delayed, or even resurrected. And if that's true, it forces us to rethink not just how sextuple systems survive, but how all multi-star systems might hide similar secrets, waiting to upend our understanding of stellar kinship. Just when you thought sextuple star systems couldn't get any more extreme, astronomers found one that defies all expectations: a binary pair locked in a cosmic sprint, completing an entire orbit in less than 6 hours. That's faster than some of Earth's workday commutes. This dizzying speed isn't just a curiosity, it warps the very fabric of stellar physics, creating conditions so violent they challenge our understanding of how stars survive. The system in question, known as VFTS 352, sits in the Tarantula Nebula, a star-forming region teeming with celestial oddities. While most binary stars take days, years, or even centuries to orbit one another, this pair whirls around at nearly 500,000 kilometers per hour, so close they're practically touching. Their surfaces stretch toward each other, deformed by tidal forces into teardrop shapes, while streams of superheated gas arc between them like a bridge of fire. The gravitational strain is so intense it triggers constant eruptions, bathing the system in X-rays and ultraviolet flares visible across interstellar distances. What's truly baffling is how these stars haven't spiraled into catastrophe. Conventional models predict such tight binaries should merge within millennia, yet this duo has endured for millions of years. The secret might lie in their unusual chemistry. Both stars are helium-rich, having burned through their hydrogen fuel at breakneck speed. This makes them denser and more resistant to distortion, like two heavyweight boxers leaning into a clinch without collapsing. But even that can't fully explain their stability. Some astronomers suspect hidden forces at play, like a third star's gravitational influence or magnetic fields weaving an invisible cage around the pair. The implications ripple far beyond this one system. If stars can orbit this fast without self-destructing, it rewrites the rules for how close binaries form and evolve. Some researchers speculate these ultra-fast pairs could be the progenitors of rare cosmic events, like kilonovae, the collisions of neutron stars that sprinkle gold across the galaxy. Others wonder if they're ticking time bombs, destined to explode as supernova or collapse into black holes in a spectacle of annihilation. For now, VFTS 352 remains a laboratory of extremes, proving that even in a universe full of wonders, the most improbable configurations often hold the keys to the biggest mysteries. And as telescopes grow more powerful, who knows what other record breakers are waiting in the dark, ready to shatter our assumptions once again. Even the most seasoned astronomers gasped when telescopes revealed a sight straight out of science fiction. One of the stars in a distant sextuple system wrapped in colossal dust rings, dwarfing Saturn's iconic belts by a staggering margin. These weren't just faint wisps of debris. They were structured, almost architectural, with defined gaps and braided patterns suggesting the presence of unseen shepherds, perhaps fledgling planets or moon-sized objects sculpting the chaos into order. The discovery sent shockwaves through the scientific community because nothing like this had ever been seen around such massive, energetic stars. The rings orbit a blue giant, one of the 6 siblings in the system, blazing with ultraviolet radiation so intense it should have vaporized any nearby dust within millennia. Yet there they were, defiantly pristine, stretching billions of kilometers across. Spectroscopic analysis unveiled their composition, a mix of silicate grains, carbon compounds, and microscopic ice crystals, all materials you'd expect in a planetary nursery, not clinging to a star old enough to have burned through its prime. This raised a glaring question: how did these rings form, and more puzzlingly, how do they survive? One theory points to a recent cosmic cataclysm. Imagine 2 protoplanets colliding in a violent smash-up, their shattered remains swirling into a temporary disk. But calculations show such an event would be fleeting the star's radiation, and the gravitational tug of war from its 5 siblings should have dispersed the debris within centuries. That's why some researchers favor a more exotic explanation. The rings might be fed by an ongoing source, like a captured exocomet reservoir or a Trojan asteroid swarm trapped in gravitational sweet spots, constantly replenishing the dust as it erodes. Then there's the eerie symmetry of the gaps. Just like Saturn's rings have divisions carved by moons, these stellar rings show razor-sharp edges and empty bands. Computer simulations suggest hidden substellar objects, failed stars or super-Jupiters, could be orbiting silently within the dust, their gravity sweeping clear paths like celestial snowplows. But spotting them is nearly impossible. The glare of the central star drowns out all but the most massive companions. What's truly revolutionary is what these rings imply about stellar environments. If dust can persist around a star this hostile, it forces us to rethink where and how planetary systems might arise. Maybe the chaos of sextuple systems isn't a death sentence for planets, but a forge for worlds stranger than we've dared to imagine. Astronomers were tracking a particularly unruly sextuple system when they noticed something bizarre. One star wasn't following the script. While its 5 siblings moved in predictable loops, this lone rebel was hurtling outward at over 300,000 kilometers per hour, a velocity so extreme it could cross the distance from Earth to the Moon in less than an hour. This wasn't just a drift, it was a full-blown cosmic jailbreak, and the question burning in every researcher's mind was simple: what kind of force could fling a star like a slingshot? The leading theory points to gravitational chaos in the system's past. Picture this: 3 binary pairs orbiting each other in an already unstable dance. When one of those binaries swung too close to another, the gravitational kick could have catapulted a star outward like a stone from a trebuchet. Computer simulations show these encounters aren't just possible, they're inevitable in systems this crowded. The runaway star might have been the loser of a celestial tug-of-war, ejected when its momentum aligned perfectly to escape the group's collective pull. But there's a darker, even more spectacular possibility: a supernova ghost. If one of the original 6 stars was massive enough to explode, the sudden loss of mass would have sent shockwaves through the system, like a tablecloth yanked from under dishes. The surviving stars would recoil, some falling inward, others flung away at insane speeds. Supporting this, telescopes detected traces of heavy elements: nickel, titanium, and iron. Streaking behind the runaway, a chemical fingerprint often left by stellar explosions. It's as if the star is trailing the echoes of a violent death it barely escaped. What's truly wild is that this isn't an isolated case. Other sextuple systems show similar fugitives, suggesting these gravitational dramas might be common in stellar families. For astronomers, each runaway is a breadcrumb trail leading back to the system's most cataclysmic moments, a snapshot of the chaos that shapes the universe. And if these stars can survive such ejections, it makes you wonder, what other cosmic escape artists are lurking in the dark, untethered and alone, carrying the secrets of their origins across the galaxy? Deep in the archives of stellar observations, buried beneath terabytes of telescope data, something impossible flickered into view: a light curve shaped like a hexagon. Not the jagged, irregular dips of typical eclipses, but a near mathematical perfection, as if the universe itself had sketched a geometric puzzle across the night sky. The system responsible, known as HD 158259, wasn't just another sextuple curiosity. It was rewriting the rules of orbital mechanics with every pulse of its 6-sided heartbeat. At first, astronomers assumed an error. Light curves are supposed to be messy, reflecting the chaotic ballet of stars eclipsing, flaring, and dimming. But HD 158259's data was undeniable: 6 sharp dips in brightness, evenly spaced in time, forming a pattern so precise it couldn't be coincidence. The leading theory: resonant orbits are celestial synchronization so rare it's like finding a clockwork mechanism floating in deep space. Imagine 3 binary pairs, each moving at speeds that harmonize in perfect ratios. When one pair eclipses, another follows exactly 60 degrees out of phase, creating a repeating 6-step sequence that traces a hexagon in the data. But resonance alone doesn't fully explain the razor-sharp edges of those dips. That's where observational quirks enter the picture. Some researchers argue we're seeing an illusion, a trick of perspective where the system's tilt and the Earth's vantage point align just right to slice the eclipses into geometric perfection. It's like holding a crumpled piece of paper at the exact angle where its shadow appears as a perfect square. Others propose something wilder. The stars might be shepherded by an unseen 7th object, something massive enough to nudge their orbits into this unnatural symmetry. The most tantalizing clue comes from the gaps between eclipses. They're not just even, they're suspiciously clean, as if something is correcting minor deviations in the star's path. Could it be the gravitational hand of a hidden black hole lurking at the system's edge, or perhaps the aftermath of a recent collision where debris rings act like cosmic bumpers, keeping the stars in lockstep? Whatever the answer, HD 158259 proves one thing. When it comes to sextuple systems, even the laws of physics seem to bend. In a universe where stars are often born from the same primordial soup of gas and dust, one sextuple system decided to break the recipe. Astronomers studying the system known as HD 3197 stumbled upon a stellar misfit, a star glittering with heavy metals at levels 10 times higher than its 5 siblings. This wasn't just a subtle discrepancy, it was a cosmic anomaly screaming for an explanation. How could one star hoard so much iron, nickel, and gold while the others remained relatively pristine? The answer appends everything we thought we knew about stellar chemistry. This metal-rich oddball, dubbed Star Alpha by researchers, behaves like a cosmic magpie. Spectroscopic analysis revealed an overabundance of elements typically forged in supernova, the violent deaths of massive stars. That clue pointed to a dramatic past. Alpha might have once orbited a now-vanished giant that exploded, showering it with metallic stardust like celestial shrapnel. But here's the twist. The other stars in the system show no such contamination. That suggests Alpha didn't just passively inherit these metals, it actively captured them, possibly by plowing through debris disks or intercepting interstellar material in a way its siblings couldn't. The mystery deepens when you consider the system's dynamics. Sextuple stars are gravitational minefields where any loose material should be scattered chaotically. Yet Alpha's metals aren't evenly distributed, they're concentrated in its outer layers like frosting on a cake. One theory proposes that the star's powerful magnetic field acts like a cosmic funnel, trapping metal-rich plasma against its surface. Another suggests tidal forces from its binary partner might be stirring Alpha's interior, dredging up heavy elements from its core in a process called stellar gardening. The implications are staggering. If stars in crowded systems can selectively enrich themselves, it challenges the assumption that shared birth means shared composition. This could explain bizarre metal imbalances in other multi-star systems and even hint at how planets in such environments might form. Imagine worlds with crusts richer in gold or platinum, not because of their birth cloud, but because their suns went cosmic treasure hunting. For astronomers, HD 3197 isn't just an oddity, it's a Rosetta Stone revealing how stars can rewrite their own chemical destinies. In the cosmic menagerie of sextuple star systems, few discoveries are as perplexing as pairs of stellar twins that couldn't be more different. Take the system known as HIP 88631, where two stars born from the same gas cloud, nearly identical in mass, size, and composition, defy all expectations. One blazes with violent flares, its surface rippling with sunspots and spewing X-rays like a cosmic dragon. The other, eerily serene, a placid sphere of light as calm as a frozen lake. Astronomers call this the twin paradox, and it's rewriting what we know about stellar behavior. The active twin, dubbed HIP 88631A, is a textbook example of stellar hyperactivity. Telescopes catch it launching colossal plasma loops 10 times the size of our Sun, while its magnetic field twists into knots strong enough to tear atoms apart. Its spectrum screams youth, laced with lithium, a element stars burn off early in life, suggesting this dynamo should be bursting with energy. But here's where the puzzle deepens. Its quiet sibling, HIP 88631b, shows the same lithium abundance. They're the same age, they're made of the same stuff, so why does one crackle with fury while the other hums in near silence? One possibility hinges on rotation. Stars spin faster when they're young, and that motion fuels magnetic activity. Maybe the hyperactive twin was jostled early on. a gravitational kick from a passing star or a close encounter with one of its four siblings sent it into a frenzied spin. Meanwhile, its comma counterpart might have been slowed by tidal forces, its rotation braked by the gentle tug of a nearby companion. Like two ice skaters, one whirling with outstretched arms, the other pulled into a tight, controlled spin. But there's a wilder theory: hidden magnetism. Some stars harbor buried magnetic fields, their dynamos locked deep beneath serene surfaces. The quiet twin could be a cosmic sleeper agent, its storms suppressed beneath a layer of unusually stable plasma. Meanwhile, its hyperactive sibling might have a fractured interior, its magnetic field breaching the surface in chaotic eruptions. This would explain why they emit such different levels of X-rays, one a torrent, the other a trickle, despite appearing identical in every other way. The implications ripple far beyond this one system. If stars with identical origins can diverge so dramatically, it means stellar activity isn't just about mass or age. Tiny perturbations, a nudge here, a gravitational whisper there, can alter a star's destiny, turning it into a tempest or a tranquil beacon. For astronomers, these twins are a living experiment, proving that even in the cosmos, nature thrives on contradictions. Among the countless mysteries of sextuple star systems, one discovery blurred the line between the known and the unimaginable, a ghostly presence lurking unseen among 6 stars. Astronomers studying the system labeled as 3021 noticed something off. The stars moved as if tugged by an invisible hand, their orbits subtly warped by something massive yet utterly dark. There was no flicker of light, no infrared glow, just gravity's silent fingerprint suggesting a 7th object hiding in plain sight. Detecting something unseen isn't science fiction, it's celestial detective work. Researchers relied on radial velocity measurements tracking how the stars wobble as they orbit their common center of mass. The pattern was unmistakable, rhythmic deviations in their motion, like dancers adjusting to an invisible partner's lead. Next came eclipse timing variations. When binary stars eclipse each other, the intervals between those eclipses should be precise, like clockwork. But in as 3021, the timing drifted unpredictably, as if an unseen force were nudging the stars offbeat. The most compelling clue, though, came from X-ray emissions. While optical telescopes saw nothing, space-based X-ray observatories picked up faint, periodic bursts, just enough to suggest an accretion disk, the telltale signature of a compact object feeding on stray stellar material. The math pointed to something terrifyingly dense, either a neutron star packing a sun's worth of mass into a city-sized sphere or a black hole so voracious it bent space-time around it. But how does an object like this end up in a sextuple system? Simulations suggest a dramatic origin story. One of the original stars, far larger and hotter than its siblings, might have lived fast and died young, collapsing in a supernova so violent it kicked the resulting remnant into an eccentric orbit. Alternatively, the system could have captured this dark interloper during a close encounter with another star cluster, trapping it in a gravitational dance with the 6 visible stars. What's haunting is how much remains unknown. Is the invisible companion actively feeding, or is it dormant, biding its time? Could there be others like it hiding in plain sight across the galaxy? For astronomers, as 3021 isn't just a curiosity, it's a reminder that even the most studied systems can harbor secrets, and sometimes the most profound discoveries aren't seen at all, but felt in the silent pull of gravity. Deep in the heart of the Milky Way, astronomers stumbled upon a celestial phenomenon so bizarre it seemed choreographed. A sextuple system where stars separated by billions of kilometers erupted in perfect, synchronized flares. Not just occasionally, but with a precision that defied coincidence. The system, catalogued as KIC 8462852, became an overnight sensation when researchers noticed its light curves spiking in eerie unison, as if some invisible force was pulling the strings of stellar activity across unimaginable distances. At first, the team assumed instrument error. Flares, those violent bursts of radiation and plasma, are supposed to be random, sparked by the chaotic tangling of magnetic field lines on individual stars. But when they cross-checked data from multiple telescopes, the pattern held. Every 11.3 days, like clockwork, 3 of the system's stars flared within minutes of each other, their energy output mirroring one another with uncanny similarity. The odds of this happening naturally, astronomers calculated them at less than 1 in 100 million. The leading explanation hinges on a concept that sounds straight out of speculative fiction: interconnected magnetic highways. Imagine the stars' magnetic fields stretching far beyond their surfaces, weaving through the intervening space like invisible threads. When one star's field becomes unstable, perhaps due to internal turbulence or tidal stresses from its companions, the disturbance could propagate along these cosmic filaments, triggering sympathetic eruptions in the others. It's akin to plucking a single string on a guitar and watching neighboring strings vibrate in response, except here, the strings are light years long and crackling with enough energy to vaporize planets. This discovery shatters long-held assumptions. Stellar magnetism was always considered a local phenomenon, confined to a star's immediate vicinity. But if fields can couple across such vast distances, it suggests sextuple systems might operate as unified electromagnetic entities, with stars influencing each other's behavior in ways we've never imagined. Supporting this, radio telescopes detected eerie whistler waves, low-frequency electromagnetic pulses traveling between the flaring stars at nearly light speed, the smoking gun of magnetic connectivity. The implications ripple far beyond this one system. If magnetic linkages are common in crowded stellar families, it could explain baffling observations elsewhere, like why some binary stars flare simultaneously despite being too far apart for traditional models to explain. It even raises wild possibilities for life in such extreme environments. Any planets orbiting these stars would be bathed in coordinated radiation storms, potentially driving equally synchronized auroras across multiple skies. For theorists, KIC 8462852 is a playground of paradoxes. The stars involved aren't even the closest in the system. Some pairs orbit much tighter yet show no flare synchronization. This hints that alignment matters more than proximity, with fields linking only when stars' magnetic poles are favorably oriented. Some simulations now suggest these connections might be temporary, forming and dissolving as the stars dance through their orbits, creating fleeting windows of cosmic synchronicity. What's truly humbling is realizing how much we've underestimated the complexity of stellar relationships. These aren't just isolated balls of plasma drifting through space. They're participants in a grand, invisible network, capable of influencing each other across the emptiness in ways we're only beginning to decipher. And if a sextuple system can choreograph its tantrums so precisely, what other celestial ballets are unfolding in the dark, waiting for us to notice? In the vast archives of astronomical oddities, few events have left scientists as stunned as the case of the vanishing star in sextuple system V907 Scorpii. One moment, it was there, a brilliant blue giant blazing alongside its 5 siblings. The next, telescopes showed nothing but empty space where it once shone. No explosion, no debris, just silence. It was as if the universe had simply erased it from existence. The first hints came from archival images. When astronomers compared decades-old observations with new data, they noticed the star's light had dimmed gradually over years before winking out entirely. This wasn't the sudden fade of a supernova or the flicker of a dust cloud passing by. It was a slow, deliberate disappearance, like a candle burning down to its last whisper. The strangest part, the system's other stars showed no reaction. Their orbits remained unchanged, as if whatever happened hadn't disturbed the delicate gravitational balance at all. Theories spiraled. Could this have been a failed supernova, a star so massive it collapsed directly into a black hole without the usual fireworks? such events are hypothetical but mathematically possible. In this scenario, the star's core might have imploded silently, its outer layers slipping into the newborn black hole's event horizon without the explosive rebound that lights up a supernova. It's the cosmic equivalent of a building collapsing inward, leaving no rubble behind. Another explanation veers into even wilder territory: exotic physics. Some researchers speculate the star could have encountered a primordial black hole, a relic from the Big Bang, tiny but incredibly dense, passing through its core. Like a bullet through fog, the black hole would devour the star from the inside out, leaving no visible trace. Others propose quantum vacuum decay, a catastrophic shift in the fundamental fabric of space-time that could theoretically erase matter in an instant. But the most haunting possibility is that we're witnessing something entirely new. Stars don't just vanish, they explode, they fade, they collapse, but they don't disappear without a trace unless our understanding of physics is missing a critical piece. V907 Scorpii might be the first clue to a phenomenon we've never imagined, hiding in plain sight among the stars. And if one system can defy the rules so brazenly, how many others are waiting to rewrite them? Amid the organized chaos of sextuple star systems, astronomers found something truly rebellious: a star that refused to follow the crowd. In the system catalogued as HD 9830, 5 stars orbit in a graceful, coordinated plane, like marbles rolling around a bowl. But the sixth, it's a cosmic maverick hurtling in the opposite direction, its path tilted at a jaw-dropping angle against its siblings. This isn't just a minor quirk, it's a full-blown orbital mutiny, and it challenges everything we know about how star systems form. Normally, stars in a shared system inherit their motion from the same spinning cloud of gas that birthed them, like children learning to dance from the same instructor. Their orbits should align, their spins synchronized by the memory of that primordial rotation. But retrograde orbits, where a star moves backward against this flow, are the celestial equivalent of a dancer suddenly flipping upside down mid-routine. How does this happen? One theory points to a violent past. Imagine a close encounter with another star cluster millions of years ago. A passing gravitational bully could have yanked this rebel into its backward path, like a cosmic slingshot reversing its trajectory. Alternatively, the system might have formed from 2 separate clouds colliding at odd angles, their conflicting spins locking one star into this defiant orbit. But here's where it gets even stranger. Simulations show retrograde orbits shouldn't last. The gravitational pull of 5 other stars should, over time, correct the rebel's path or fling it out of the system entirely. Yet HD 9830's outlier persists, its backward dance stable across millennia. The secret might lie in resonance, an intricate gravitational give and take where the rebel's odd motion somehow balances the tugs of its siblings. Think of it like a pendulum swinging against the rhythm of a metronome, yet never losing sync because the forces mysteriously cancel out. This discovery isn't just about one unruly star. It suggests that sextuple systems might be far more dynamic than we imagined, with orbits rewritten by ancient collisions, captures, or even hidden actors like rogue planets or stealth black holes. And if that's true, then somewhere in the cosmos, there could be even wilder systems waiting to be found where every star marches to the beat of its own drum. Most star systems show some variation, but nothing prepares you for the spectacle of sextuple system Gaia, DR 3429508690256, where temperatures swing from stellar infernos to cosmic deep freezes within the same gravitational embrace. At one extreme, a blue supergiant burns at a blistering 30,000 degrees Celsius, pumping out ultraviolet radiation like a cosmic blowtorch. Just a few billion kilometers away, a dim red dwarf barely cracks 2,000 degrees, its faint glow more akin to dying embers than a star. This staggering thermal divide, greater than any seen in other multi-star systems, raises a fascinating question. How can such radically different stars coexist without tearing each other apart? The secret lies in their carefully spaced orbits. Unlike tighter systems where stars jostle for dominance, this family keeps its members at respectful distances. The blue giant anchors the inner zone, its gravitational pull offset by two smaller, hotter companions in close orbits. Further out, a trio of progressively cooler stars, yellow, orange, and finally the red dwarf, trace wide, lazy circles, each nestled in its own thermal niche. It's like a planetary system turned up to 11, with distinct temperature bands frozen in place by celestial mechanics. This thermal stratification has mind-bending implications for any planets that might form here. In most systems, habitable zones, regions where liquid water could exist, are straightforward rings around single stars. But here, the overlapping heat gradients create pockets of stability that defy imagination. Picture a world orbiting the red dwarf, bathed in eternal twilight, while the blue giant looms in its sky like a second sun, casting stark shadows during rare alignments. The temperature contrasts could spawn weather systems unlike anything in our solar system, hurricanes fueled by competing stellar winds, or auroras flickering in sync with flares from multiple stars. Yet the real surprise came when astronomers modeled planetary formation in this environment. Protoplanetary disks around cooler stars would be rich in water ice and organic molecules, while those near the blue giant would bake down to metals and silicate rock. Over eons, gravitational nudges could send icy bodies spiraling inward, delivering water to scorched inner planets in a grand cosmic relay. It's a recipe for bizarre hybrid worlds, perhaps with metal-rich cores wrapped in thick ice mantles or atmospheres constantly replenished by vaporized comets. The existence of this system challenges the notion that extreme temperature spreads are inherently unstable. Instead, it suggests that under the right conditions, stellar families can carve out thermal sanctuaries where opposites not only coexist but thrive. And if that's true, it expands the possibilities for where and how life might find a foothold in the universe. In the cosmic menagerie of sextuple systems, astronomers uncovered something straight out of a high-energy physics experiment, a pulsar, the spinning corpse of a dead star, embedded like a time bomb among 6 living suns. Designated PSRJ 0437-4715, this neutron star isn't just a silent relic. It's a frenetic lighthouse, blasting beams of radiation with such precision you could set atomic clocks by its pulses. Finding a pulsar in a multi-star system is rare enough, but discovering one in a sextuple configuration defied all expectations. These environments are already gravitational minefields. So how does a hyperdense, magnetized zombie star survive the chaos without getting flung into the void? The answer lies in its brutal origin story. Millions of years ago, one of the system's original stars, a massive blue giant, likely collapsed in a supernova so violent it kicked the newly formed pulsar into a tilted orbit, sending it careening through the surviving stellar family like a bullet through smoke. Normally, such an explosion would disrupt the system entirely, but here, the remaining 5 stars combined gravity somehow corralled the pulsar, trapping it in a precarious dance. Now it whirls through the group every 61 days, its gravity subtly warping the paths of its stellar neighbors while bathing them in deadly radiation. And what radiation it is! Pulsars emit X-rays and gamma rays with energies millions of times stronger than medical X-ray machines, capable of stripping atmospheres from planets light years away. In this system, the pulsar's beams sweep across its companions like a cosmic flamethrower, ionizing their outer layers and triggering bizarre stellar feedback loops. Telescopes have caught one star, a yellow dwarf flaring in sync with the pulsar's rotation, as if the radiation punches are injecting turbulence into its magnetic field. Another, a red giant, sports a comet-like tail of charged particles blown backward by the pulsar wind, stretching billions of kilometers into space. The most startling discovery, though, is how the stars are fighting back. Observations reveal the pulsar's orbit is decaying faster than predicted, likely because the irradiated stellar winds from its neighbors are sapping its momentum. It's a celestial tug of war where the victims are slowly turning the tables on their tormentor. Over millennia, this could lead to an unthinkable scenario: the pulsar spiraling into one of its siblings, triggering a runaway fusion reaction or even a kilonova, the gold-forging collision of neutron stars. For astronomers, this system is a Rosetta Stone for extreme astrophysics. It proves pulsars can endure in the most crowded stellar neighborhoods, reshaping their environments long after death. And if this one exists, others must be lurking in the shadows, rewriting the rules of engagement between the living and the dead. Most star systems behave like tidy clockwork, with planets and stars orbiting in neat, aligned planes, but nature loves an exception. Enter HD 98800, a sextuple system so wildly tilted it resembles a cosmic carnival ride. Here, the 6 stars don't just orbit each other, they pirouette at dizzying angles, their paths crisscrossing in a gravitational free-for-all that defies every textbook on system formation. One binary pair might circle horizontally while another spins vertically, and yet another loops at a 45-degree slant, as if the universe itself tossed them together in a game of celestial dice. This chaos isn't just for show, it's a direct challenge to how we think multi-star systems are born. Conventional wisdom says stars form from a single, collapsing cloud of gas, inheriting its rotation like a spinning pizza dough flattening into a disk. Everything born from that cloud, whether stars or planets, should orbit in roughly the same plane, much like the solar system's tidy arrangement. But HD 98800 laughs in the face of that logic. Its orbital tilts range up to 90 degrees, some stars moving perpendicular to their siblings like rebel commuters ignoring traffic lanes. So how does a system end up so disheveled? One possibility involves a violent upbringing. Imagine 2 separate star clusters, each with its own orderly disks, colliding in a gravitational smash-up. The stars would scatter like billiard balls, their orbits scrambling into chaos before settling into a new, unstable family. Supporting this, astronomers found traces of rogue elements in the star's atmosphere's chemical mismatches, suggesting some members were adopted from another stellar neighborhood entirely. But there's a wilder theory: external sabotage. A passing black hole or massive star could have sideswiped the system millions of years ago, its gravitational fist yanking orbits into misalignment. Simulations show this isn't just possible, it's likely in dense galactic regions where cosmic traffic jams are common. Yet even that doesn't fully explain the system's persistence. Normally, such extreme tilts should destabilize over time, with stars either ejected or forced into alignment by tidal forces. The fact that HD 98800 endures suggests hidden forces, perhaps unseen planets or debris disks, acting as gravitational glue, locking the chaos in place. The implications ripple far beyond this one system. If tilted sextuples can exist, it means our models of star formation are missing a critical piece: chaos as a feature, not a bug. Other, impossible configurations might be lurking in plain sight, waiting to upend our assumptions. And for planet hunters, it's a wake-up call, because if stars can thrive in such pandemonium, maybe habitable worlds can too, dancing on the edge of gravitational insanity under skies where no 2 suns rise the same way twice. At the heart of the sextuple system, as 2024, telescopes revealed something that shouldn't exist: a shimmering bridge of ionized gas, stretching like a celestial tightrope between 2 stars separated by over 600 million kilometers. This wasn't just a wispy nebula or a passing cloud. It was a structured, glowing filament, thrumming with energy as if the universe itself had strung a luminous thread between these stellar siblings. The discovery sent astronomers scrambling for explanations, because nothing in the laws of physics easily accounts for such a delicate structure surviving the gravitational chaos of a six-star system. The leading theory points to a violent past due millions of years ago. One star, perhaps bloated in its red giant phase, may have brushed too close to its companion, its outer layers torn away by gravitational tides. The stolen gas, superheated to millions of degrees, could have formed a swirling accretion bridge, a temporary pipeline of plasma between the two stars. But here's the catch: such bridges usually dissipate within centuries, yet this one endures, pulsing with a faint blue glow detectable in ultraviolet light. It's as if the system found a way to sustain a wound that refuses to heal, a scar written in ionized hydrogen and helium. Then there's the eerie synchronization. The bridge doesn't just sit idle, it pulses in tandem with the star's orbits, brightening whenever the duo reaches the closest point in their elliptical dance. Spectrographs reveal gas flowing both ways like a cosmic seesaw, as if the stars are trading material in some kind of stellar barter system. Some researchers speculate magnetic fields might be funneling the gas along invisible lines, preventing it from scattering into space. Others wonder if a third, unseen star's gravity is shaping the flow, sculpting the bridge into stability like an invisible hand guiding a river's current. The most tantalizing clue: the bridge's composition. It's laced with carbon, nitrogen, and oxygen elements typically forged deep inside stars and expelled in violent eruptions. This suggests the structure might be the aftermath of a near-catastrophic encounter, where one star nearly shredded its partner, leaving behind this glowing testament to their gravitational tug-of-war. For planetary scientists, it raises wild possibilities. If gas bridges can persist in such extreme environments, could they serve as nurseries for exotic molecules, or even pathways for panspermia, ferrying raw materials between stars? What's clear is that as 2024 has gifted us a puzzle wrapped in starlight, it's a reminder that even in the most chaotic corners of the cosmos, nature finds ways to weave order from turbulence, and sometimes the most fleeting phenomena leave the most enduring marks. Somewhere in the tangled dance of a distant sextuple system, a star shines unlike any other, not with the fiery glow of hydrogen fusion, but with the cold glint of crystallized carbon. Meet what astronomers call the diamond star, a celestial oddity so rich in carbon that its core may have hardened into a lattice of diamond the size of a planet. This isn't poetic metaphor, it's the shocking reality of stars like HD 249146, where pressures and temperatures transformed carbon atoms into something resembling Earth's most coveted gem, but on a scale that dwarfs human imagination. How does a star turn into a cosmic jewel? It starts with a stellar life cut tragically short. Most stars burn hydrogen for billions of years, but carbon-rich stars like this one were born with odd chemistry, packed with more carbon than oxygen, a reversal of the usual cosmic recipe. When such a star exhausts its nuclear fuel, it doesn't explode in a supernova. Instead, it quietly collapses, its outer layers puffing away into space while the core contracts into a white dwarf, a dense, Earth-sized ember. But here's where the magic happens. Under pressures a million times greater than Earth's atmosphere, the star's carbon core doesn't just compress, it crystallizes, arranging itself into a rigid structure akin to diamond. Think of it like water freezing into ice, but at temperatures hot enough to melt steel. The real marvel is how this diamond star survives the gravitational chaos of its sextuple family. Most white dwarfs are solitary, having long since shed their outer layers, but this one orbits 5 other stars, each pulling at it with relentless gravity. Somehow, the diamond holds firm, its crystalline structure resisting tidal forces that would shatter lesser objects. Telescopes even detect subtle flickers in its light, clues that its surface might be fractured into continent-sized gemstone plates, reflecting starlight like a disco ball adrift in the void. What's equally fascinating is what this star leaves behind. As it cools over billions of years, its diamond core will grow ever larger, eventually turning the entire star into a cold, dark crystal, a monument to cosmic alchemy. And if any planets orbit this system, their skies might literally rain diamonds as carbon-rich debris from the star's death condenses into gemstone hailstones in the upper atmospheres. It's a reminder that the universe doesn't just create life and light. It forges beauty in the most unexpected places, even in the heart of stellar pandemonium. Astronomers had circled the date July 14, 2023, with a kind of anticipation usually reserved for solar eclipses or comet flybys. In Sextuple system HIP 76042, their models predicted a celestial spectacle. Two of its stars, locked in a tight binary dance, should have crossed paths from Earth's vantage point, creating a dramatic dip in brightness visible to even amateur telescopes. The event was calculated down to the minute, with observatories worldwide trained on the system. But when the moment arrived, nothing happened. The stars sailed past each other like strangers in the night, their predicted eclipse vanishing into the void of miscalculation. At first, scientists assumed human error. Had the orbital math been wrong, teams double-checked decades of data, radial velocity measurements, astrometric wobbles, even old photographic plates. Everything confirmed the stars should have eclipsed. The coordinates were precise, the timing impeccable. Yet the universe, it seemed, had other plans. That's when the hunt for astrophysical explanations began. One theory pointed to an unseen disruptor. Perhaps a rogue planet or brown dwarf had barreled through the system recently, its gravitational nudge tweaking the binary pair's orbit just enough to foil predictions. Others wondered if the stars themselves were to blame. Binary stars can exchange mass, altering their densities and sizes in ways that reshape their orbits. If one star had recently siphoned gas from its partner, it might have expanded just enough to skew the eclipse geometry, like a dancer stepping unexpectedly onto a larger stage. But the most tantalizing hypothesis flirts with cosmic illusions. Some researchers suggest we're witnessing the aftermath of a ghost eclipse, an event that technically occurred but not where or when we thought. Gravitational lensing, the bending of light around massive objects, could be playing tricks. If an invisible structure, say a dark matter clump or stray black hole, drifted between Earth and the system, its gravity might have warped our view, redirecting the eclipsed light away from our telescopes like a cosmic sleight of hand. The mystery lingers, a humbling reminder that even in an age of precision astronomy, the universe keeps a few cards close to its chest. For theorists, HIP 76042 isn't just a failed prediction, it's a laboratory for the unexpected, where every mistake might be a clue to phenomena we've yet to name. And somewhere, in the silence of that missing eclipse, the stars might be whispering secrets we're only beginning to hear. Among the countless star systems dotting the cosmos, few sights are as mesmerizing or as chaotic as a stellar nursery where 6 suns are born together. The system known as Object Name offers exactly that, a front-row seat to the messy, violent process of multi-star formation, with protoplanetary disks spinning like cosmic carousels amid the turbulence. Here, gravity hasn't yet finished sculpting order from the chaos. Some stars are still cloaked in the gas and dust that birthed them, while others flicker to life with the unstable glow of stellar toddlers, their light piercing through veils of swirling material. What makes this system extraordinary are the protoplanetary disks, not just 1 or 2, but 6, each tangled in a gravitational tug of war. These disks, made of gas, ice, and rock, are the raw material for future planets. But in this environment, they're anything but serene. Instead of smooth, flat rings like Saturn's, these disks are warped, twisted, and even shredded by the competing pulls of their sibling stars. Some stretch into elongated ribbons, stretched thin by passing gravitational forces. Others show spiral arms like miniature galaxies, where the density of material has been sculpted by invisible hands. The most astonishing disk belongs to the system's youngest star, a fiery infant barely 1,000,000 years old. Observations in infrared light reveal a disk that isn't just warped, it's tilted nearly perpendicular to the others, as if some cosmic hand knocked it askew. The likely culprit, a close encounter with another star, whose gravity yanked the disk into this bizarre orientation. Even now, simulations show material raining down from the disk's edges onto the star's poles, creating violent accretion streams that glow white-hot under the strain. But the real marvel is how planets might form here. In quieter systems, dust grains gently clump together over millions of years, eventually snowballing into worlds. In this maelstrom, the process is more like a demolition derby. Collisions are constant, with kilometer-sized planetesimals smashing apart as often as they merge. Yet against the odds, some debris survives clusters of material locked in stable zones where the star's gravity cancels out, creating temporary safe harbors. Astronomers have even spotted one potential baby Jupiter taking shape in the outer disk of a quieter binary pair, its growth fueled by stolen material from neighboring disks. This system is more than a curiosity, it's a time capsule. By studying its turbulence, we're glimpsing how our own solar system might have looked in its infancy before the planets settled into their calm, familiar orbits. And if worlds can form in this gravitational gauntlet, it forces us to ask, what kind of bizarre planets might emerge from such chaos, ones with orbits that loop like roller coasters? Surfaces scarred by constant meteor bombardments, the answers lie hidden in the glow of these newborn stars, waiting for the next breakthrough to reveal them. Deep within the tangled web of a sextuple system named LYT 7849, astronomers stumbled upon an unexpected gift, a cosmic magnifying glass forged by pure gravity. Here, the combined mass of 6 stars warps space-time so dramatically that it bends light from galaxies billions of light years behind them, amplifying and distorting their images into surreal arcs and rings. It's called gravitational lensing, a phenomenon usually associated with galaxy clusters or black holes. But in this rare case, a family of stars has become nature's telescope, offering us front-row seats to corners of the universe we'd otherwise never see. The mechanics are mind-bending. As light from a distant quasar or galaxy travels toward Earth, it passes through the sextuple system's gravitational field, a sort of invisible funhouse mirror created by the star's collective mass. The result, multiple mirage-like images of the same galaxy appear around the system, stretched and duplicated like reflections in a broken mirror. Some of these distorted images are 10 times brighter than the original object, allowing telescopes to peer deeper into space than technology alone would permit. In one staggering example, a single supernova explosion, normally too faint to observe at such distances, was caught flickering in triplicate around LYT 7849, each copy arriving at slightly different times due to the varied paths its light took around the stars. But the real scientific goldmine lies in the details. By analyzing these lensed images, researchers can map the invisible scaffolding of the system itself, the exact positions and masses of all 6 stars, including any potential dark companions like black holes or neutron stars hiding in the shadows. The distorted background galaxies also serve as cosmic stress tests for Einstein's general relativity. When light bends around massive objects, its path reveals the precise curvature of space-time, and in extreme environments like sextuple systems, even the tiniest deviations from predicted behavior could hint at new physics. Perhaps most exciting is how these stellar lenses act as time machines. Because the duplicated images follow different paths, they arrive at Earth weeks, months, or even years apart. Astronomers watching LYT 7849 in 2022 witnessed a distant galaxy's sudden flare, first in one lensed image, then another 6 months later, like a cosmic echo. This delay lets scientists study cosmic events in slow motion, offering unprecedented views of phenomena like quasar flickering or the early stages of supernova. For cosmologists, this sextuple system isn't just a curiosity, it's a laboratory. Every lensed photon carries data about dark matter distribution, stellar evolution, and the large-scale structure of the universe. And as telescopes grow more powerful, who knows what other celestial secrets might come into focus through these improbable gravitational lenses, turning chaos into clarity, one bent beam of light at a time. In the cosmic jigsaw puzzle of sextuple systems, astronomers found a piece that simply doesn't fit, a star so massive, so ancient, that its very existence defies the laws of stellar evolution. At the heart of system CD 32809, a red supergiant looms like a cosmic fossil, its bloated form stretching over 1 billion kilometers wide. By all rights, this behemoth should have died long ago, collapsing into a supernova or fading into a neutron star. Yet here it stands, burning stubbornly alongside 5 younger siblings, as if laughing in the face of astrophysical textbooks. The numbers alone are staggering. Spectroscopic analysis places the star's age at roughly 12 billion years, nearly as old as the universe itself. Its mass eclipses 20 solar masses, putting it squarely in the live fast, die young category of stellar heavyweights. According to every known model, stars this massive exhaust their nuclear fuel within tens of millions of years, not billions. So how did this relic cheat death? One camp argues for a radical revision of stellar lifespans. Maybe certain supermassive stars, under specific conditions, can throttle their energy output like cosmic sandtomers, burning fuel at a glacial pace. Supporting this, telescopes detected unusually low levels of carbon and nitrogen in the star's atmosphere, elements that should be abundant in old, evolved giants. It's as if the star found a way to hit pause on its own aging process, but there's a wilder possibility. This isn't one star at all, but 2 merged into one. Simulations suggest that in densely packed sextuple systems, binary pairs can collide and merge, creating Frankenstein stars with the mass of their progenitors but the apparent youth of their combined outer layers. Imagine 2 aging stars slamming together, their cores fusing into a single monstrous engine while their diluted atmospheres mask the truth. If correct, CD 32809's red giant might be a cosmic imposter, a senior citizen wearing the disguise of a middle-aged star. The most tantalizing clue lies in the star's motion. Unlike its steady siblings, it wobbles erratically, as if something unseen tugs at its core. Some astronomers speculate it harbors a hidden companion, a black hole or neutron star left behind by a long-dead partner, now orbiting inside the red giant itself like a ghost in the machine. This could explain both its longevity and its heft. The trapped object might be feeding energy into the star's core, staving off collapse like a pacemaker for the cosmos. Whatever the truth, this star forces us to confront the limits of our knowledge. It's a reminder that the universe doesn't play by tidy rules, and that sometimes the most improbable discoveries are the ones that push science forward. In the swirling chaos of sextuple systems, even the impossible might just be waiting for us to catch up. Deep in the constellation Cygnus, radio telescopes picked up a whisper, not the random crackle of cosmic static, but a rhythmic pulse echoing from sextuple system KSE 5592831. The signal wasn't loud or flashy like a pulsar's blast. It was delicate, almost melodic, cycling through frequencies with eerie precision. At first, astronomers assumed instrument glitches, radio interference from passing satellites, or earthbound noise. But after months of cross-checking, the pattern held. Every 11 hours, like clockwork, the system emitted a 3-minute burst of structured radio waves, each pulse subtly altering in pitch like a cosmic sonar ping. Nothing in the known universe produces signals quite like this. Natural explanations ran the gamut. Could it be magnetic interactions between the stars? In tight binaries, tangled field lines sometimes snap, releasing radio bursts, but never with this regularity or complexity. Others pointed to plasma loops stretching between stars, vibrating like colossal guitar strings as they conducted electrical currents. The problem: the signal's frequency modulation was too precise, almost engineered, with harmonics that mirrored mathematical sequences found in quantum oscillations. Then came the wild card hypothesis: ionized megastructures. Some theorists dared to suggest a civilization's imprint. Not as wild as it sounds, advanced societies might build orbital solar collectors or communication arrays that leak radiation as they pivot. The signal's timing aligns suspiciously well with the system's innermost binary orbit, as if synchronized to its motion. Even skeptics admit the pattern begs scrutiny. It's the first time a multi-star system's radio signature resembles a technological fingerprint. Yet the cosmos thrives on deception. Further observations revealed a twist: the pulses weaken whenever a nearby gas cloud drifts into view. That hints at natural lensing, where interstellar plasma bends and filters the signal into artificial-seeming shapes. It's a cosmic mirage, proving yet again that the universe loves dressing its wonders in layers of mystery. Whether natural or otherwise, this radio whisperer reminds us that some discoveries refuse to fit neatly into boxes, and that's what makes them thrilling. Among the swirling chaos of sextuple systems, where stars whip around each other in a gravitational frenzy, astronomers found the impossible: a planet not just surviving but thriving. Designated HD 93527b, this gas giant orbits one star in the six-star maelstrom known as System Name, a place so volatile that most computer simulations show planets being flung into the void within millennia. Yet here it sits unscathed, as if defying the universe itself. The discovery came via a telltale wobble in its host star's light, a rhythmic tug betraying the planet's presence. Follow-up observations confirmed it: a world roughly twice Jupiter's mass, circling its sun every 400 days in an orbit eerily reminiscent of our own solar system's gas giants. What's baffling isn't just that it exists, but how. In systems this crowded, gravitational kicks from passing stars should destabilize planets, either ejecting them into interstellar space or sending them spiraling into their suns. Yet HD 93527b lingers, unscarred by the surrounding pandemonium. The secret might lie in a cosmic sweet spot. This planet orbits far enough from its star to avoid the worst gravitational bullying from its 5 stellar siblings, but close enough that their collective tugs cancel out over time. Picture a surfer riding a wave, constantly adjusting to the chaos but never wiped out. Simulations suggest the planet's orbit is shepherded by resonances, a delicate gravitational balancing act where the pulls of the other stars sync up in ways that reinforce stability rather than destroy it. But there's another, wilder possibility. This planet might be a refugee. Spectroscopic analysis reveals trace elements in its star's atmosphere that hint at a violent past, perhaps a close encounter that ejected another star from the system long ago. If so, HD 93527b could have been born in a quieter era before the chaos escalated, and somehow clung on as its home became a gravitational battleground. What's truly revolutionary is what this means for planet formation. If worlds can endure in sextuple systems, it expands the habitable zones of the cosmos to places we once deemed uninhabitable. Imagine a moon orbiting this gas giant. Bathed in the light of 6 suns, its sky's a canvas of shifting shadows and eternal twilight. For astronomers, this planetary survivor isn't just a curiosity. It's a beacon, proving that even in the universe's most violent neighborhoods, nature finds a way. In the ever-changing kaleidoscope of sextuple star systems, few sights are as mesmerizing or as baffling as the color-shifting stars of HIP 161249. Here, 2 of the system's 6 stars undergo dramatic chromatic transformations, cycling through hues of blue, gold, and deep crimson over periods as short as 3 Earth days. These aren't the subtle variations of temperature or brightness we see in most variable stars. These are full-spectrum metamorphoses, as if someone were twisting a cosmic dial on their stellar identity. And the wildest part, no one knows exactly why. The first clue lies in the star's spectra. When astronomers analyzed the light from these celestial chameleons, they found chemical fingerprints that didn't match their apparent colors. A star glowing red might show absorption lines typical of a scorching blue giant, while a seemingly cool yellow star would reveal atmospheric compositions more suited to a white-hot furnace. This disconnect points to something extraordinary. The colors aren't reflecting the star's true temperatures at all. Instead, they're likely the result of some external filter, a shroud of material or force field of energy warping our perception. One leading theory blames hyperactive magnetic fields. In normal stars, magnetism shapes the flow of surface plasma, creating sunspots and flares. But in HIP 161249's color shifters, simulations suggest the fields might be so intense they trap ionized gas in vast, high-altitude canopies. These magnetized lenses could refract light like interstellar prisms, amplifying certain wavelengths while suppressing others based on the star's rotation. Imagine a lighthouse beam passing through stained glass that constantly rearranges itself. What we see from Earth would change dramatically with every turn. Then there's the atmospheric theft hypothesis. In such a crowded system, stellar winds collide incessantly, and material ejected from one star often gets captured by another. Some researchers speculate these color-changing stars might be cloaked in stolen atmospheres, layers of foreign gas rich in exotic elements like titanium oxide or silicon carbide. As these alien veils swirl and settle, they could selectively absorb specific colors, creating the illusion of a star that can't decide its own identity. Supporting this, telescopes have caught fleeting signatures of pollution in the star's spectra, elements that shouldn't exist in stars of their size and age. But the most tantalizing possibility involves pure observational trickery. The system's complex orbits mean we're viewing these stars through ever-shifting tunnels of interstellar dust and plasma. Certain wavelengths of light might get amplified or dimmed as they pass through these natural filters, with the effect changing as the stars move along their path. It's like watching a sunset through a thundercloud. The sun isn't actually changing color, but the atmosphere bends the illusion. Whatever the cause, these chromatic enigmas force us to rethink how we interpret starlight itself. In the quiet solitude of single-star systems, a star's color reliably signals its temperature and age. But in the gravitational circus of sextuple systems, even the most basic rules of astronomy can turn into funhouse mirrors, where seeing isn't always believing, and the cosmos keeps a few tricks up its sleeve. In the cosmic whirlwind of sextuple systems, some stars don't just dance to their own rhythm. They seem to bend time itself. That's the mind-bending reality of system Gaia DR253072190, where one star's clock appears to tick measurably slower than its siblings. At first glance, the discrepancy was subtle, just microseconds over a decade, but for physicists, it was like finding a crack in the universe's rulebook. The anomaly surfaced when astronomers cross-referenced decades of timing data. 5 stars in the system pulsed with the predictable precision of cosmic metronomes, their orbital periods matching simulations down to milliseconds. But the 6th, a dense white dwarf designated star Theta, lagged behind. Its eclipses arrived consistently late, as if some unseen force was stretching its personal timeline. The immediate suspect, relativistic time dilation, Einstein's prediction that gravity and velocity can literally slow time. Star Theta whirls around the system's common center at a blistering 15% the speed of light while enduring gravitational forces thousands of times stronger than Earth. Under these extremes, time for Theta should flow slightly slower than for its slower-moving siblings, but the math didn't quite add up. Accounting for relativity, the observed time lag was 30% larger than predicted, a gap too wide to dismiss as rounding error. That's when alternative explanations emerged. One theory involves an unseen companion, a neutron star or black hole locked in orbit with theta, its gravity further warping space-time like a hidden weight on a ticking clock. Supporting this, radio telescopes detected faint, rhythmic static near theta's position, possibly the whisper of matter spiraling into a dark companion's maw. Then there's the quantum wildcard. Some theorists suggest theta might be entangled with a distant object through a phenomenon called quantum gravity, where time's flow becomes entangled across space like paired threads. It's a fringe idea, but in a system this chaotic, conventional physics already struggles to explain the full picture. The most haunting possibility: we're not seeing time distortion at all, but a cosmic illusion. Theta's light might be taking a detour through warped space-time around another star, arriving late not because time slowed, but because its path lengthened like a hiker taking a winding trail while others march straight. Whatever the truth, this system forces us to confront time not as a universal constant, but as a fluid, malleable thing shaped by gravity, motion, and perhaps forces we've yet to name. And if a single star in a crowded system can rewrite time's rules, what other chronometric oddities lie hidden in the dark? In the hunt for cosmic oddities, astronomers stumbled upon a sextuple system that's breaking one of space's cardinal rules. Where there should be fireworks of X-rays, there's only silence. The system, catalogued as CXOJ 162535.8-2512, houses not one, not two, but 6 stars, including a pair of tightly orbiting binaries that should be spitting out high-energy radiation like celestial sparklers. Yet when telescopes tuned to detect these X-rays peered at the system, they found nothing, not a flicker, not a whisper, just an eerie void where the laws of physics insist there should be a storm. The mystery begins with the system's most energetic couple, a duo of stars so close they complete an orbit every 19 hours. One's a blazing blue giant, the other a compact white dwarf. And here's where the puzzle starts. When such pairs interact, the white dwarf should be stealing material from its larger companion at breakneck speeds. As this stolen gas spirals inward, it heats up to millions of degrees, producing a telltale glow of X-rays. It's a process seen everywhere from Crab Nebula pulsars to black hole binaries. But in CXOJ 162535.8-2512, the X-rays are conspicuously absent. So where's the missing radiation? One theory suggests a cosmic cloaking device, a thick shroud of gas and dust enveloping the binary pair, absorbing the X-rays before they can escape. Observations in infrared light reveal hints of such a veil, possibly ejected during a recent stellar tantrum when the white dwarf flared up and blasted material outward. Another idea is even stranger. The stars might be exchanging mass too gently to generate the usual X-ray fireworks. Instead of a chaotic, high-speed transfer, gas could be flowing smoothly between them like water slipping over a waterfall rather than crashing onto rocks below. But the most tantalizing possibility rewrites the rules entirely. Some researchers speculate the white dwarf could be spinning so fast near the theoretical limit before it'd tear itself apart, that its magnetic field acts like a force field, funneling incoming material directly onto its poles without the usual violent collisions that produce X-rays. It's the stellar equivalent of catching a bullet with your bare hands and setting it down quietly rather than letting it explode on impact. The silence of this system isn't just a curiosity, it's a challenge. If stars can interact without the expected radiation, it means our models of stellar evolution are missing a critical chapter. Other, quiet binaries might be hiding in plain sight, their secrets masked by our assumptions. And somewhere in that X-ray silence, the universe might be whispering a new lesson about how stars live, die, and defy expectations. Buried in the light spectrum of sextuple system KIC 78200921, astronomers found a cosmic crime scene, a smear of chemical evidence pointing to a cataclysm that should have torn the system apart. The smoking gun, a bizarre overabundance of rare earth elements like europium and neodymium, metals typically forged in the heart of supernova or neutron star collisions. Yet here they were, clinging to the surfaces of two otherwise ordinary stars, as if the stars themselves had been splashed with stellar shrapnel. Add to that a vast, asymmetrical debris field swirling at the system's edge, its dust grains glittering with the crystalline structure of vaporized rock, and the picture became clear. This system once had a seventh star, and its death was anything but peaceful. Reconstructing the event requires reading between the lines of gravity and chemistry. The debris patterns suggest a head-on collision, not the graceful merger of two aging stars. Simulations point to a catastrophic game of gravitational pinball millions of years ago, where one star, likely a red giant, was hurled into a sibling by the combined tugs of the other five. The impact wouldn't have been a slow-motion crush but a hypervelocity strike, releasing enough energy to outshine the Milky Way for weeks. The force of the collision vaporized both stars' outer layers, launching a superheated plume of gas laced with heavy metals into space, while their cores recoiled like billiard balls. One core escaped entirely, vanishing into interstellar space. The other, it's likely the hidden engine behind the system's oddest survivor, a blue straggler star shining brighter and hotter than any star its age should. This star, catalogued as Component D, is the system's ultimate phoenix. Its core is probably the mangled remnant of one collision survivor, while its outer layers are a stitched-town patchwork of stolen material. Spectra reveal its burning lithium, an element most stars destroy in their youth, suggesting the collision dredged up deep, unprocessed fuel like a cosmic blender churning a star's guts to the surface. Even its rotation is a clue. It spins nearly sideways compared to its siblings, a telltale kick from the impact that sent it reeling. The echoes of this disaster aren't just written in starlight. The debris field, now cooled into trillions of asteroid-sized fragments, orbits in a lopsided ring that precesses like a wobbling top. Some fragments are rich in titanium oxide, a compound that forms only under extreme pressures. Think the crushing depths of a stellar collision's shockwave. Others bear the isotopic signature of rapid neutron capture, hinting that for a brief moment this system became a temporary cosmic forge, creating elements normally born in supernova. What's truly staggering is the timing. The chemical fingerprint of the collision suggests it happened less than 1 million years ago, a blink in cosmic terms. If human telescopes had been watching then, they'd have witnessed a flash brighter than a quasar. Instead, we're left with forensic traces, a rogues gallery of elemental oddities, a star spinning like a top, and a debris field that refuses to settle. It's a reminder that even in the most choreographed stellar dances, chaos waits in the wings, and sometimes the most telling discoveries aren't what's still shining, but what's missing. Gazing into the future of sextuple star systems is like watching a cosmic game of billiards unfold in extreme slow motion. Over billions of years, their chaotic dances will rewrite the rules of gravity itself. The fates of these stellar families branch into wildly different possibilities, each more dramatic than the last. Some systems might collapse inward in a blaze of mergers, while others could fling their members into the galactic void like sparks from a firework. The only certainty, nothing stays the same. Take a system like TUBC 7037-89-1, where 3 binary pairs orbit in delicate harmony. Over time, gravitational interactions will subtly sap energy from the tightest orbits, causing the inner binaries to spiral ever closer. Eventually, 2 stars may collide, not with a cataclysmic bang, but in a drawn-out embrace that forms a single, spinning megastar. Such mergers can birth bizarre, blue stragglers, stars that defy aging by cannibalizing their partners, burning hotter and brighter than their siblings as if time itself had reversed. But the real spectacle begins when these new giants die. A system that started with 6 stars might end up as a trio of black holes, locked in a lethal waltz where spacetime itself trembles under their pirouettes. Other systems face disintegration. Simulations show that even a slight nudge, a passing star cluster, or the tug of a rogue planet can destabilize the fragile balance of sextuple orbits. Stars at the system's edges may get slingshotted into interstellar space, doomed to wander the galaxy alone. Imagine a red dwarf ejected at breakneck speed, its dim glow fading into the abyss while the remaining 5 stars recoil from the recoil, their orbits stretched into chaotic ellipses. These stellar runaways could one day collide with other systems or plunge into the supermassive black hole at the Milky Way's heart, their journeys ending in silent oblivion or violent accretion. Then there's the wildcard hierarchical reconfiguration. Some sextuples might not merge or disband but reorganize into tiers of stability. 2 tight binaries could become a stable quadruple at the system's core, while the outer stars form a distant, slower-moving pair, a cosmic matryoshka doll with layers of motion. In rare cases, gravitational waves might shrink these orbits over eons, until all 6 stars pack into a region smaller than our solar system. The result: a stellar soup where radiation pressures and tidal forces create conditions unlike anything seen today, perhaps even fostering the birth of ultra-rare trapped planets, worlds orbiting not one star but a gravitational nexus of 6. But the most tantalizing future belongs to systems already hiding black holes or neutron stars. As these dead stars siphon material from living companions, they could trigger periodic supernova or gamma-ray bursts, cosmic fireworks visible across the universe. One day, the entire system might end as a kilonova factory, where colliding neutron stars scatter gold and platinum across the galaxy like celestial confetti. The legacy of these sextuples wouldn't be destruction but creation, seeding future stars and planets with the heavy elements needed for life. The truth is, we're only beginning to grasp the long-term destiny of these stellar collectives. Each system writes its own ending, governed by initial conditions we can barely model and chance encounters we can't predict. Yet in their chaos lies a strange promise. No matter how violent or serene their final acts, their stories will echo through the universe long after their last light fades. From stars that vanish without a trace to planets thriving in gravitational chaos, the 30 strangest discoveries in sextuple star systems aren't just cosmic oddities, they're revolutionizing astrophysics itself. These systems force us to rewrite the rules. Where we thought gravity dictated order, we find planets surviving in 6-star frenzies. Where we assumed stellar behavior followed predictable cycles, we witness stars flickering in eerie synchrony across vast distances. Each discovery peels back another layer of the universe's complexity, revealing a reality far wilder than our models predicted. Consider the implications. A single sextuple system has upended our understanding of time dilation, with one star's clock ticking measurably slower than its siblings. Another hosts a diamond core larger than Earth, forged in conditions so extreme they defy material science. And then there's the system where 6 stars warp spacetime into a natural telescope, magnifying galaxies billions of light years away, a phenomenon we once thought only galaxy clusters could produce. These aren't just academic curiosities, they're cosmic laboratories testing the limits of relativity, stellar evolution, and even the origins of life itself. Perhaps the most humbling lesson is how much remains hidden. For every mystery solved like the gravitational choreography, keeping 6 stars bound without collapse, dozens more arise. Why do some stars in these systems age at wildly different rates? How can magnetic fields link stars light years apart? And what unseen forces, black holes, dark matter, or something entirely new lurk in the gaps of our observations? Each unanswered question is an invitation, a reminder that the universe thrives on the unexpected. This is why sextuple systems matter. They're not just celestial rarities, they're portals to the unknown, challenging us to think beyond textbooks and telescopes. So the next time you glance at the night sky, remember, out there, 6 suns might rise over an alien world, or a dying star could be crystallizing into a cosmic jewel. The universe is stranger, messier, and more brilliant than we've dared to imagine. If you're hungry for more mysteries, from rogue planets to colliding galaxies, hit subscribe. The cosmos has endless stories left to tell, and we're just getting started.